Okay, so before I move on, I'm going to make a quick detour and talk about incompatible observables. In classical mechanics, quantities such as position, momentum, energy, and angular momentum are number valued. They have definite defined values. In quantum mechanics, these quantities are replaced by Hermitian operators acting on quantum states and are called observables. So, what in classical mechanics is the quantity A is replaced by an operator A hat acting on the quantum state psi. Well, there's only certain states psi for which our operator acts like it's multiplying our state by a number. So only some states for which A hat behaves like a number, or some states where A hat has definite value, so to speak, like it would in classical mechanics. And these particular states are called the eigenstates, a special subset of states called the eigenstates of the operator A hat. And the definite values that they take on are called the eigenvalues of that operator. So, in our space of states, there's a special subset of states which are eigenstates of A hat. That is, they have definite number valued A. And there's another subset of states for which the quantity B is also definite. The eigenstates of the operator B hat. Well, if you want a state which has both definite number values of A hat and B hat, then our subsets must overlap with one another, and which means that there must be some states psi such that they are eigenstates of both A hat and B hat. So let's write B hat acting on psi. This is the hypothetical eigenstate of both A hat and B hat, is going to be equal to lambda sub B acting on psi. Now let's act, when lambda sub B is a constant, now let's act A hat on that. Hey, that rhymed. That's just a constant, so it'll be pulled out here. And by definition, it'll be an eigenstate as well of A hat, so it's going to be lambda B, lambda A, psi. So A acting on B acting on psi is just lambda A times lambda B times psi. Now what if we did this in the other direction? Let's act A hat on psi equals lambda A times psi. Now let's act B on from the outside here. That's just a constant, it'll be pulled out to the side. That by definition is just lambda A times lambda B times psi. Now these are just constants. They're not operators, they're numbers. And so the order of which you multiply them doesn't matter. So lambda B times lambda A is equal to lambda A times lambda B. Well, let's subtract both sides of these equations. These are the exact same. So you get A hat B hat minus B hat A hat times psi equals 0. Well, we know our state's not 0. That would be redundant. That wouldn't be very fun. So that means that if our operators A hat and B hat, this is called their commutator, and if their commutator goes to 0, then they can share eigenstates, which means that there are states for which A hat and B hat both have number values. And if their commutator is not 0, or they don't commute, then there's no states for which both A and B have definite values. For example, let's consider position and momentum. Let's say A hat is our position operator and P hat is our momentum operator. Let's take the commutator of these operators. Well, we defined our momentum operator as negative I h bar times the derivative with respect to x. And this argument generalizes to 3D as well, or any dimension, or any unit choice. So we're going to take the commutator of x hat with negative I h bar times the derivative with respect to x. We're going to get rid of the hats here. And we're going to apply a test function here. So x, okay, we're going to pull out the negative h bar factor first. X well, by chain rule, that's just, with respect to x, that's just 1 minus derivative of f times x. Well, those cancel out there, and we're left with I h bar times f equals x with p times f. We can pull out the test function, and we find out that the commutator of x of the position operator with the momentum operator is I h bar. That's not 0, which means that there are no states for which the position has a definite value and the momentum has a definite value. The popular statement of the Heisenberg uncertainty principle is that if you don't know the position, or if you know the position, then you don't know the momentum, and if you know the momentum, you don't know the position. That's not a very good way of saying it, because uncertainty implies that there is value, you just don't know which one. You're uncertain as to which one. In this case, momentum and position can't both have values. It's not a statement about you're not certain which value. It's a statement about one has value, or one can have value, and one doesn't. One's just an operator and one's a number in certain states. So the uncertainty principle isn't really a particularly good name for it. And in fact, and I'll show this in a later video, the generalized uncertainty principle, I think, the generalized uncertainty principle, the uncertainties, as they're called, are actually just another name for standard deviation. And I'll show that in another video on the probability interpretation of quantum mechanics at some point. But yeah, I thought it would be a good idea to go over incompatible observables, because the concept is important to the development of our theory of angular momentum in quantum mechanics.